Hi everyone, this is Mrs. GA and today we're going to learn about the chain rule. Alright, I have a quick warm up for you guys, so please pause the video and hit play when you're ready to check. Alright, go ahead and check your work. So here we're kind of working from the outside in, and notice that the most outer function we would call f of x, and then we work inward to g of x and even j of x if it's possible. So for the first one, the outer function would just be x to the power of 10. And then the inner function, g of x, would be 3x squared minus 5. For part B, our outer function, if you kind of zoom out the most, it'd be e to the x, and then you could see that we're plugging in sine of x to that. So that would be g of x. For part C, this is actually, we can write it as a composition of three functions. So if you zoom way out, it's simply a rational function, 1 over x. And then within that, you could see that we have a radical function. So our g of x would be cube root of x. And then within that, we have our polynomial function, x cubed minus 1. And then part D is a little tricky. This is actually three separate functions as well. Remember when we write cosecant cubed of 2x, it's saying the cosecant of 2x cubed, the whole thing cubed. So if you zoom out the most outer function would actually be that cubic function. And then within that, we have our trig function cosecant of x, and then within that, we have our linear function 2x. Now, understanding this composition of functions is going to be absolutely critical to us working with what's called the chain rule, which helps us to differentiate a composition of functions. So if we have y equals f of u, which is a differentiable function of u, so y is differentiable in terms of u, and then u is defined as g of x, where u is a differential function of x, then we could say that y equals f of x, which f of u, which equals f of g of x. So if we have this composition of functions that are differentiable in respect to their relative variables, we can find the derivative of that composition by doing f prime of g of x times g prime of x. So if you break this down into the different parts, the first part right here is the derivative of the outer with respect to the inner. So we have to first identify what that outermost function would be. We take the derivative of that outermost function, but we leave the inner. So we leave that g of x as whatever it is. And then we do the second part, which is we multiply it by the derivative of that inner function. So this is our chain rule. Again, it helps us find the derivative of a composition of functions, and we can actually continue this chain pattern for the composition of as many functions as we have. So sometimes maybe it's a composition of 3 or 4. We can kind of just continue this pattern of working our way in. So again, as we did in the warm-up, to use this chain rule, it's really, really important that we are able to identify the inner and the outer function. So I just want to look at 3 examples really quick. So if we have y equals the sine of x squared. So if I zoom as far out as I can, the thing that I see on the outer would be our trig function, our sine of x. So our outer function here is sine of x, and then within that, the inner function is that x squared. Now, if you look at the second one, it looks very similar, but you'll notice that here our sine function is being squared. So if we kind of think of it as this, we can see that our outer function in this case is actually the quadratic, and the inner is that trig function. Now, if we look at this third example, there's actually 3 functions going on here. So if you zoom the farthest out, again, you'd see that quadratic function. So the most outer would be x squared. And then I'll say the middle for this one. The middle would be our trig function, our sine function. And then even within that sine function, we can see that we have another inner function, which is that 2x, that linear function. So again, we always are going to be starting working our way from the outer all the way in as far as we need to go. All right, so before we start using our chain rule, let's do a proof of our chain rule. So we are going to use that limit process as we usually do to do this proof. So let's do the limit as x approaches a, and then we're using this as our function. So we have f of g of x minus f of g of a all over x minus a. So before, well, if you try to do direct substitution here to evaluate this limit, we get that indeterminate. So we know we need to do a little manipulation to help us evaluate this limit. Now, just to kind of give us a hint of where we might be trying to go, or so this proof makes more sense as we go through, I just want to write what each of these individual things would look like in that limit form. So if I was to look at this portion right here, I would describe that as saying the limit as x approaches a. Ideally, it would become f of g of x minus f of g of a all over g of x minus g of a, right? Change in y over change in x. And then if I were to create this scenario, so like in an ideal world, this portion would look like this. The limit as x approaches a of g of x minus g of a over x minus a. Right, so if we saw something like this, we would define that as g prime of x. If we saw something like this, we would define that as f prime of g of x. So if you look at what we have here, well, we have portions of each one. So you can see here we have the numerator of what we would like to see for this portion. And then here we have the denominator of what we would like to see for g prime of x. But you'll notice that something is missing. That g of x minus g of a, and really conveniently, one of those things is in the numerator and one of those things is in the denominator. So we can actually multiply our function or our limit like this by g of x minus g of a over g of x minus g of a. So I haven't changed the value because I'm really just multiplying by a form of 1. And now if I just rearrange where we write things just for convenience, f of g of a. So I'm going to move this one over to this side, g of x minus g of a. And it's a product, so I can move it wherever I want. And then g of x minus g of a is going to stay on the top. And then here we have x minus a. So by rearranging those terms, I see that this, by definition, equals that f prime of g of x, because again, it's that change of y over change of x. And then this portion would actually turn into g prime of x. So I can rewrite those as f prime of g of x times g prime of x. So here we have just proven the chain rule. So sometimes, when we're doing proofs, especially the first time we're learning them, it is kind of useful to look at where we're trying to go, and that could give you a hint of the step we need to take. But hopefully this makes sense when we kind of break it down into these two portions and then kind of work our way backwards. Kind of cheating for proofs, but hopefully it helps you kind of understand why we want to do this step of multiplying by g of x minus g of a over g of x minus g of a. So now that we also know the chain rule, we can have a more general form of the power rule we've learned before that we've been using a lot, but now we can use the power rule with a composition. So just the general form of the derivative of u to the power of n would be n times u to the power of n minus 1, and then times u prime. So if u is another function, we would just take the derivative of that function. So again, this is just the more general power rule now that we know that chain rule. All right, so let's give this chain rule a try. So we're going to find the derivative of the following two functions. So for this first one, y equals the sine of x squared plus 1. Remember, we start on the outside. So our outermost function is that sine function. So I'm going to start by taking the derivative of our sine function, which we know is cosine. But again, we're going to maintain that inner function here. And now we're going to look at that inner function, which is our quadratic, x squared plus 1, and we're going to take the derivative of that. So the derivative of x squared plus 1 is just 2x. So it's the cosine of x squared plus 1 times 2x. We do want to make sure that it's very clear that this 2x is not part of our trigonometric function. So let's just write it out front. And there is our derivative. All right, let's look at part B. So again, it might be helpful to remember that this really just means the cosine of x to the power of 5. So in this case, we can actually see that our outermost function would be like x to the power of 5. So it's a power rule function. So we're going to actually do that portion first. So if I were to use the power rule, right, you take your exponent, you move it out front, or you multiply it by whatever constant is there. And then we are going to subtract our exponent by 1. So it becomes cosine to the power of 4 of x. So 5 times cosine to the power of 4 of x. And then we're going to take the derivative of our inner function, which is the cosine function. And that derivative is negative sine of x. So we can just take our negative and move it out front with the 5. Sorry, I forgot the prime here. So our derivative is negative 5 times cosine to the 4th of x times sine of x. And here you go. So just be careful when you see something written like this. Remember, our outermost function would actually be x to the power of 5. So we use power rule. And then our inner function would be that cosine function. So here are our two derivatives. All right, now let's give these two a try together. So for each of these, you'll actually see that there's actually a composition of 3 functions. So there's an outer, a middle, and an inner. So for part A, we can see again that our outer function would actually be that x to the 5th function. So we're going to start with that. So we'd use our power rule. So again, we do 5 times cosine to the power of 4 of 3x. So we've done our outermost function and we left the inside. And now let's look at the next portion of our function, which would be our cosine function. So our cosine function, the derivative of that is negative sine. And then we're going to leave the inner portion of that, which is 3x. But then we need to keep working our way in until we've made it all the way in. So our last portion, the most inner portion, is that linear function, the 3x. So now we need to do the derivative of this one. And the derivative of 3x is just 3. So again, first we did power rule. So that was the 5 cosine to the power of 4. Notice that we left the cosine in the 3x. Then we took the derivative of cosine, which is negative sine, but we left the 3x. And then we took the derivative of 3x, which is just 3. So overall, our derivative would be negative 15, because we have the negative, and then the 3 times the 5, and then cosine to the power of 4 of 3x, and then sine of 3x. This is a 4. Okay, let's take a look at part B. So for this one, again, we have a composition of 3 functions. If you zoom out the most, you'll see that the e to the x would be our outermost function. So we know that the derivative of that, of e to the x, is just e to the x. So here's our derivative, but notice that we're leaving the inner portion the same. And then we look at the inner portion. The next, I guess we would say the middle function would be our sine function. So the derivative of sine is cosine, but I'm still leaving the 2x. And then I look within that and I take the derivative of our most inner function, that 2x, and the derivative of that is 2. So our derivative will be 2 times e to the power of sine of 2x times cosine of 2x. All right, so now I have one for you to try on your own. So pause the video and give it a shot. All right, go ahead and check your work here. So again, we have a composition of 3 functions. That outermost function is actually the cubic function, so we'll use our power rule. So you'll notice that the 3 moved to the front and our exponent decreased by 1. And then our next innermost function would be our cosecant function. And the derivative of cosecant is negative cosecant cotangent. But notice it stayed 2x on the inside. And then we could take the derivative of our innermost function, that linear function, which is just 2. And then we just are going to multiply. So we have the negative times the 2 times the 3. And it is all a product. So we have cosecant squared of 2x times cosecant of 2x. So that actually is just cosecant cubed of 2x times cotangent of 2x. All right, so now we're going to try to find a derivative of a function that will require both the chain rule and the product rule. So here you can see we have f of x equals x squared times the sine of 4x. So there's 2 portions of our function here. There's this function, x squared, and then we have sine of 4x. So it's the product of those 2 functions. And then within this portion here, we will need to use our chain rule when it's time to find the derivative of this portion. So remember, for our product rule, it's first function times the derivative of the second. So now to do the derivative of the second, we have to use that chain rule. So the derivative of sine is cosine, and then the derivative of 4x is 4. So we've done first function times derivative of second, and then plus second function times the derivative of the first, which does not require the chain rule. It's just 2x. So we can see that f prime of x is 4x squared times the cosine of 4x plus 2x times the sine of 4x. And we can also, from this, you'll notice there is a common factor of 2x, so we can factor that out. So we have 2x times the cosine of 4x plus the sine of 4x. So that is f prime of x. All right, let's try another one where we have to use product and chain rule. So again, you can see we have the product of a cosine to the 4th and cotangent of 7x. And because this function is a composition of cotangent and 7x, we will need to use the chain rule here. And because this function is actually a x to the 4th and then a cosine function, we will also need to use the chain rule here. So we'll need to use the chain rule for both of them in addition to that product rule. So to find y prime, again, we're going to break it down with our product rule. So we do first function, so the cosine to the 4th of x, times the derivative of the second. So for the derivative of the second, the outermost function is our cotangent function, and the derivative of that is negative cosecant squared. And then we're taking the derivative of the inner function, which is just 7. So we've now done first times derivative of second plus second, which is cotangent of 7x, times the derivative of the first. So the outermost function here is that polynomial, so the x to the 4th. So we're actually going to need to do chain rule for first. So 4 times cosine cubed of x. And then we're going to do the derivative of the innermost function, which is the cosine function. And the derivative of cosine is negative sine. So there we have it. And I think I need one more parenthesis there. All right. So now we're just going to try to kind of simplify what we have. So for this first portion, we have negative 7 cosine to the 4th of x. Cosecant squared of 7x. And then here we have, I'll do minus 4 times cosine cubed of x, sine of x, cotangent of 7x. So you can see for these types of functions or derivatives, it's really important that first you have all of your derivative rules memorized. Like you shouldn't really need to think too hard about what the derivative of cotangent or cosine is. And it's also really important that you have your product and your quotient rules down and you have those memorized as well, because when you have problems where you need to use multiple rules in one, you really just need to make sure you know all of your individual rules and you just take it one step at a time. All right, so I have another one for you to try on your own. So please pause the video and give it a shot. All right, go ahead and check your work here. So you can see that this is the product of two functions, and then within each individual function, they're both compositions, so you would need to use the chain rule for those individual derivatives. So here I have first times the derivative of the second. So you say use the power rule, and then I found the derivative of the quadratic also using power rule, plus second times the derivative of first, kind of similar. And then for the rest is really just kind of reorganizing and simplifying. So here I just multiplied, the 5 and the 6x. Here I just multiplied the -1 and this 3. And then I noticed that there is a GCF of 3 times 1 minus x squared times 3x squared minus 5 to the 4th. So we just factored out the GCF, and then the remaining expression you can just distribute and combine like terms. So it looks really ugly, but really after the first step, it's just kind of simple algebra to kind of tidy up your derivative. All right, so let's try another one together. So here, this looks like a function where you say, oh no, we need to use the quotient rule and the power rule. But actually, every once in a while, you can kind of rewrite a function to help you avoid having to do that extra work of a power rule or of a product rule or a quotient rule. So in this one, we actually don't need to use the quotient rule. If we rewrite this as, instead of 1 over something, we could say that this is actually x cubed minus 1 to the power of -1/3. So the negative exponent kind of flips the term, and notice that I rewrote cube root of x as to the power of 1/3. So you can see that now I don't need to use the quotient rule. I will still need to use our chain rule because we have a composition of functions, but it does make it a little bit easier. So always look for ways that maybe you can rewrite your original function to make it a little bit simpler. You could do the quotient rule here, but it would definitely take you a little bit longer. So now let's do our chain rule. So our outermost function is that x to the power of -1/3. So we have -1/3 times x cubed minus 1 to the power of -4/3. And then we're going to take the derivative of our innermost function, so it just becomes 3x squared. So y prime, if you multiply these two terms, we just get -x squared times x cubed minus 1 to the -4/3. And here, let's just rewrite it so we don't have any negative exponents. So we have -x squared over x cubed minus 1 to the 4/3. And there you go. So just a little tip to look out for this. Sometimes you are able to rewrite the function. Sometimes you're not, and you will need to work through a more tedious problem. All right, I have another one for you to try on your own. Pause the video and give it a try. And for this one, you will need to use the quotient rule in addition to the chain rule. All right, go ahead and check your work here. So here you can see our outermost function is that x to the power of 6. So we use our power rule here. So 6 times all of this to the power of 5. And then to take the derivative of our innermost function, we do need to use our quotient rule here. So remember, low d high minus high d low, all over low squared. And then from here, it's really just a matter of kind of simplifying through. So here I kind of split up the numerator and denominator. Remember, each of these are raised to the power of 5. And here you actually have the same factor. So x squared plus 3 to the power of 5 times x squared plus 3 squared becomes this. Then we're just kind of simplifying until we end up with this final answer for our derivative. So now that we know our chain rule, we can actually use it to find a new derivative. We can find the derivative of a to the power of x, where a, again, is just some value. So it's our exponential function. So before we do that, I want to talk about another way to rewrite a to the power of x. So let's look at this expression. E to the power of natural log of a. This does simplify to just a, because here, remember, our bases match. It's base e and natural log is base e. So this will simplify to a. So if I want to find a way that I can write a to the power of x, well, I know that a is equal to this, so I can just say e to the natural log of a to the power of x. And then we could rewrite that as e to the natural log of a times x, because our rule when you raise a power to a power is just to multiply your exponents. So a to the x can be written as this. So if I'm finding the derivative, if I want to find the derivative of a to the x, well, I don't know how to do that. But I do know how to find the derivative of e to the natural log of a times x, because we can actually find this derivative using our chain rule. So here, let's start with our outermost function. Our outermost function is e to the power of x. So we're going to take that derivative, which is also just e to the power of x. So remember, our inner function is going to stay the same. And then according to chain rule, we now take the derivative of our innermost function, which is the natural log of a times x. Remember, natural log of a is just some value, right? A is just a value. So natural log of a is a constant, technically. So imagine this said 2x. If I asked you, well, what's the derivative of 2x? You would tell me 2. So if I say, what's the derivative of the natural log of a times x? It's just the natural log of a. So just remember that the natural log of a is just a constant. Just like a is also a constant. So here we have our derivative. We can simplify it a little bit more because we know that e to the natural log of a is just a. So this just becomes a to the power of x times the natural log of a. So this is actually our derivative. So d dx of a to the power of x. So this is our derivative of any non-e base exponential function. So here it is again. Here's the derivative of our exponential function that is not base e. So this is another one that you will definitely want to memorize. So again, the derivative of a to the x is just a to the x times the natural log of a. So whatever your base is, it goes inside your natural log. Now let's see if we can use this new rule to help us find these derivatives. So here we just have y equals 3 to the power of x. So in this case, that a is now 3. It's base 3. So if we want to find y prime, it's just 3 to the power of x times natural log of 3. So pretty simple and straightforward. Here in part B, you'll see that we will actually need to use our chain rule here because we have our base 8 function, and then within our exponent we have another function. So to do our chain rule, first we're going to take the derivative of our outermost function, which would be 8 to the power of x. So we have 8 to the power of 1 minus x squared times natural log of 8. And now we're going to want to multiply that by the derivative of our inner function. So here, we're using chain rule. And the derivative of 1 minus x squared would just be negative 2x. So here, our derivative is negative 2x natural log of 8 times 8 to the power of 1 minus x squared. And I'll put a little product symbol in there. There you have it. All right, I have one last example for you to try on your own, so please pause the video and hit play when you're ready to check. All right, so go ahead and check. Here you can see for our chain rule, the outermost function is that exponential base function. So we have 2 to the power of x squared times natural log of 2. That's how you do the derivative of our exponential function. And then we'll multiply that by the derivative of our inner function, which is just 2x. And then I just rewrite it to look like this. All right, so that is all for today's video. Thank you so much for watching.